Okay, so I'll start now. And right, allegedly I'm continuing, sort of continuing the previous plan, but it's always hard to tell because it seems like I'm starting from the scratch each time. Right, well, so one big arc that this is part of is we're allegedly trying to follow this story that starts with the ideas of the art and reciprocity theorem. And then it turns into or ascends towards the Jugendtraum ideas, Kronecker's Jugendtraum, and ideas falling from that. This is all allegedly part of that, but somehow we've really gotten into analogies here between the number theory of art and reciprocity and things like child's drawings, which are a kind of branch cover of the Riemann sphere. And there's this big analogy between, is there this big, I think that, there certainly are analogies, right? Extensions of number fields are certainly analogous in some way to covering spaces of Riemann surfaces or complex projective algebraic curves. You can tell this analogy because of the way the Galois groups work. But well, so I began, well, let's see. We're going to have even more analogies. So this is perhaps, maybe we have one of these, three-way analogies or something like that. So in one of our column, we have the number fields and their extensions. In the second column, we have complex projective algebraic curves and their branch covers. And that very much includes the children's drawings and things like that we're trying to understand. And then there's this third column. I think there's this third column. It's something I've only heard kind of like from rumor. But I'm beginning to suspect that it might make sense. And it sounds like it comes from, in some very naive sense, it sounds like it just comes from adding an extra dimension onto the complex projective algebraic curves, adding an extra real dimension on. So, you're thinking of these as Riemann surfaces, if you're thinking of those Riemann surfaces, real two-dimensional, you could add a third dimension onto them. And so they would be like three manifolds or something like that. Where did the complex structure go? I don't know. But it's hard to maintain the complex structure when you've got an odd number of real dimensions lying around. But previously we had branch covers that were branched at, just points of the Riemann surface.
Yeah.
But now it seems to make sense for the branch covers to be branched at knots in the three manifold. And so it sounds like there's some analogy. I've vaguely heard this.
Yeah, I've definitely heard about this.
I may have misheard it. I may have misheard what they said, but what I seem to be being led towards here is the idea that there's an analogy. Let me try to maybe write it down. So what does it do? It goes something like number fields and primes that belong to number fields in some sense, and three manifolds of some kind, maybe compact three manifolds or something like that. And some sort of knots in them.
Mhm.
And so is there, so what do you know about this? Is there like a big analogy like this that we have to learn?
Yes, I mean, there is such a thing. It's mysterious in some ways, but I have seen some people who make very nice big charts of which start out at the top, like what you just drew. They actually draw these charts. And one of the pieces of evidence for this stuff is that
I have a couple to add. Yeah, go ahead.
the Italo cohomology of number fields has some kind of three-dimensional part to it.
An analog or part? What? A
Well, it goes up to degree 3.
I see. Oh, okay. Okay, so the cohomology looks suspiciously. Okay.
I think it was actually Barry Mazur, Artman Mazur calculated the Italo cohomology of probably like Z or something, and discovered this three-dimensionality in that number field case. And I'd love to understand more about that.
Sorry, I'm screwing up here again. I just can't find my controls here. What did I do to them? Oh, damn. It does that thing again. Well, okay, something came back. But let's see. Sorry, I'm constantly screwing up here. Okay, I think I've got what you said, but I was going to try to write down what you said, which was so a hint along these lines is that a tau cohomology of number fields has a three-dimensional aspect.
Yep. And I've always wanted to get around to really understanding that.
Well, I was going to suggest some very naive guesses about how such an analogy might work. So what was I going to say? I was going to say, I have no idea if this is really going to be on the right track, but what am I trying to say? That if you have I mean, there's this idea of things like Legendre symbol and Jacobi symbol and Artin symbol, which is going to be important in very fancy versions of the Artin reciprocity conjecture, which perhaps is the real version of the Artin reciprocity conjecture, Artin reciprocity theorem. So what like, yeah, what does, right, like the Legendre symbol says something like, when does one prime split sort of relative to another? A Legendre symbol takes in two primes and it tells you when one prime splits with respect to the other, meaning with respect to the taking the square root of the other. And then, you know, quadratic reciprocity is this mysterious quasi-symmetry of that function of two inputs. And And I'm struggling to get something like that to make sense with the knots in the three manifold. So I'm imagining I've got a knot in a three manifold, and I can take the cyclic branch cover of it. And that's, cyclic, so it's an abelian extension. And that's a very basic thing that people do when they're studying knots in three manifolds. They take the cyclic branch cover of that, right? That's how they understand things like the Alexander polynomial and stuff like that. I think I'm going by very vague memories.
It's true. It's true. Yeah.
And they do something with the cohomology. I don't know, but so I can imagine trying to do something like seeing if one knot splits in the branch cover of the other, or if it instead remains inert. But inert is misleading because something interesting happens, but it just doesn't split into two separate pieces. It sort of unwraps instead. And I'm imagining that this could somehow, does this make any sense? I'm imagining that this determining whether, I have this vague feeling that determining whether one knot splits in the branch cover of the other, cyclic branch cover of the other. Sounds like it has something to do with something like linking number or something like that.
Yes.
You have what?
Yeah. Sorry. Yes, it's people have.
I mean, I'm tempted to try to make that analogous to the Artin symbol or something like that, or the Legendre symbol or something like that. What were you going to say? I interrupted you. Go ahead.
Yeah. So there's a paper, and I'm been trying to find it by. I think it's. Can I just share my screen for a second?
Sure. Sure. Just yes. Go ahead.
Yeah,
you can take care of it. Steal it.
Yeah. So there's a paper by, I think it's this paper here by Kapranov and someone named Smirnov. So it's this paper here. And it may be this paper here. And if it is the paper, they talk about how the linking number is analogous to the, I guess, Legendre symbol. Maybe it's not this paper. I don't. But yeah, I've definitely seen people try to go in that direction. I'm not sure this is. Sorry, that I'm not. I was just. Oh, here it is. Here's this nth power residue symbol. That's.
Yeah.
They should. Well, I won't keep scouring through this paper, but they say early on. So
well, they do say Arakelov geometry, which makes me think that this is. I think the Arakelov geometry people are some of the people who talk about these analogies. But go ahead, yeah.
Yeah.
Are you talking about the field with one element? No. Well,
yeah, they are. This may, yeah. That's not the main thing I want. That's not what I wanted to.
Sure.
Get into.
Sure.
It's
I mean,
interesting.
this is already good enough. Even if you don't find anything else, this is also already a very good hint.
Yeah. So I mean, here it just says the scheme spec Z one with respect to the Zariski topology, and at least 3 with respect to the Étale cohomology. I don't know why they say at least 3, but that makes me. But anyway, this may not be the paper, but in fact, I think it's not, because I think there's another paper by Kapranov where he like hits out for early on, trying to say that like quadratic reciprocity is like connected to linking or analogous in this mysterious way to linking numbers. So
I'd really like to see that.
That.
I'd really like to see that, because I was just taking wild guesses here, and my wild guesses didn't completely make sense, but they still might be on the right track. And I was also going to mention here that I mean, we also had, what did we have? I mean, with the children's drawings or the Riemann surfaces, right? We had like a third column here, which was,
Want to share your screen again?
sure, sorry, I
can't.
forgot that I wasn't.
Yeah, can't.
Where is it here? Share
View that.
screen. Okay, I'm hoping that's
That's not it yet.
okay, but it's coming back. It's coming back. Must be here somewhere.
There. Yeah.
Okay.
Okay, a third one.
A third column, which was the column we already talked about. We were trying to make number fields analogous to like Riemann surfaces, or perhaps Riemann surfaces with Child's drawings or something like that. Riemann surfaces. And just, I mean, I guess instead of primes or knots, it would just be points or marks. Or marks. And what I was dissatisfied about with that column is that it didn't seem to, I might just be confused, but it didn't seem to offer enough opportunity for the prime analogs to split relative to each other. Right? Because I mean, one mark, you don't sort of see a mark splitting, with respect, just a point on a Riemann surface. I don't see any obvious sense of, right? It seems like of a lack of the extra dimension that the three manifolds have, the knot dimension. It almost seems like I need that extra dimension to get part of the analogy to work. So there,
by the way, you probably know this completely, but
yeah,
people do come out and say that like the three-dimensional aspect of the integers is supposed to sort of imagine that like one dimension is which prime you're at. So it's sort of a sort of semi-normal direction along the integers. And then each prime.
Well, but that's what we would call that's the mysterious dimension. That's the arithmetic dimension, right?
Okay. Okay.
I mean,
there's maybe that is the weird one. I don't know. So then there's the other dimension that's weird from some point of view, which is that like each prime you think of as like being a little hole that has a little circle that goes around it, which is connected to the Frobenius when you do.
Well, that is definitely this extra third knot dimension. I think, but I'm just confused about. Okay, I'm confused. Yeah, I'm confused about which is the weird dimension here, which is the arithmetic dimension compared to the geometric dimensions. I'll really have to think about that because it came out, something you said came out opposite of what I was expecting. But also, it still sounds like you gave me, you told me you were going to give me three dimensions, and so far you gave me two dimensions. Is that right? What was the third one?
Well, to go around a hole, you have to have two dimensions. So I'm thinking of a hole as being like a little.
Oh,
it's a loop, but it's sort of in a.
All right, I'll really have to think about that. Some things are coming out slightly.
So it's like when you have your knot, you have like the two dimensions that you can let you go around the knot, and your branch covering is like taking you to a different cover when you go in a little loop around the knot. But then there's a third direction, which is along. This may not match my other story, but this is like the third dimension, which is along the knot. Yeah, so I don't know what going along a prime is. So so it doesn't really match.
No, but I think
You think
let me think. Going along the knot. All right, I'm suffering this confusion between the longitudinal direction and the meridional direction. But right, but I have a feeling that you really need that longitudinal direction. That's so that primes can split. Frobenius. I'm gonna have to think about that, and this might be really important in trying to figure out the art and reciprocity ideas here. But anyway, so this is more vague analogies to think about. I just wanted to throw this in, and I'm really glad you came up with intelligent responses in the form of references and stuff where they may actually get some of this to make sense. Right, now I have to figure out where we're actually going here. So, well, like I say, we're definitely exploring analogies here. We're still, I think we're gonna try to really think a lot about the children's drawings today. Let's just take that attitude for the moment, that we're going to not worry so much about trying to relate it to art and reciprocity or something. We're just going to try to learn children's drawing, because we've all been working with children's drawings to some extent, but we kind of just threw ourselves into the water without really. I think I can do a little bit more systematic. I can do things. I understand things a lot better now. I can tell you a little bit more about children's drawings and stuff. I mean, there was a big mistake I made in email that was trying to fix. So so let's start trying to get somewhat rigorous about what children's drawings are, and so you can really relate them to Coxeter groups and Coxeter diagrams and stuff like that. So let me give you some Coxeter diagrams here. And we're going to have sort of homomorphisms between Coxeter diagrams. And well, so we're gonna have three Coxeter diagrams. Each of these three Coxeter diagrams is going to have 3 dots, and they're probably all 3 of these Coxeter diagrams are important in some way. But let me draw them first. So we've got one that looks like this one is very equilateral. It's got infinity on each label. And so that means that the Coxeter reflection group is just free on 3 involutions. But if you think about that, that means that the Coxeter rotation group is just free on 2 generators. I mean, you could take for the Coxeter rotation group, you could take the generators I mean, I'm being a little bit sloppy here, but it's probably okay. I mean, you could take like green, blue, and blue, red as generators, and then you wouldn't need green, red, or red, green, because that would just follow by composing green, blue with blue, red.
Yep.
So
okay.
So maybe we should call this the child's Coxeter diagram, because this is the one that really is related to children's drawings. The Coxeter rotation group is the free group on 2 generators, which is more or less what children's drawings is all about. And
is there any
yeah
connection between the 3 punctured sphere and the 3 solutions here? the thrice punctured sphere.
Yes. All right. Yes. I mean, first of all, let's just draw a little sketch of this Coxeter tiling. So it looks like am I doing this right? Et cetera, et cetera, et cetera. And now, what was your question? Well, I mean, when you start wrapping this up, you can see that you can think of, I tend to think of green as 0, red as 1, and blue as infinity. And, so when you have these tilings made out of these triangles with these green and red and blue things, made out of these triangles with green and red and blue corners, and they all fit together. I forget what I was going to say. Yes. No, I was just responding to your suggestion that, or question or whatever, that those greens and blues and reds are the fiber. The greens are the fiber over 0, the blues are the fiber over 1.
Mhm.
No, for my convention, it's better to have the blues be the fiber over infinity and the reds are the fiber over 1. Is that making sense?
I'm not trying to get the convention to make
Right,
sense.
right. But just the basic idea that yes.
So you're taking this.
Yes to your question. Yes.
So
I'm taking what?
Let's see. So this space here is some kind of branched cover of the 3 punctured sphere.
Yes, this is sort of like
Is it like
it's like the universal one, or the honor. It's the universal honorary one, because I mean it's perhaps you only allow finite branching officially, but this is the ideal limiting case, which is infinite.
Okay.
So yeah, I mean, this is the Cayley action of the free group on 2 generators. Now, I mean, because we're doing rotations rather than reflections, you have to take the fundamental regions to be a pair of these triangles stuck together. And then you have to worry a little bit about, which pairs of triangles stuck together are the fundamental regions. And the convention that we'll probably be using is that you take those, you take the red-green edges. Each red-green edge is between a pair of triangles, and so those pairs of triangles correspond to the fundamental regions. So I mean that's why the children's when you're drawing the children's drawings, you just draw the red-green edges, right? But I guess Grothendieck or whoever just doesn't call them red and green. He calls them I don't know. I've actually seen different conventions, but maybe they're black and white or something.
Sorry, what
star
are they in
and
terms of
asterisk.
what are they in terms of numbers? 0, 1, and infinity? There's 0 and 1.
Yeah, I'm thinking of green as 0 and red as 1.
Uh-huh. So the 0, 1 edges.
The 0, 1 edges, yes, the unit
Uh-huh.
intervals.
So what are you doing? You're taking two triangles, you're taking any pair of triangles that share a 0, 1 edge and you're lumping them into some square. And
I'm not sure square is the best word for it, but yeah. But
but
yes, and I'm just
yeah.
taking those as the official fundamental regions.
How does that? So because that's a sub, so because this even group, this rotation group is a subgroup of the free group on 2 generators, you're getting another cover of the 3-punctured sphere. It's like from it. It's like not a universal cover, but it's like it's double covered by the it's covered by the universal cover. And is that relevant here? That is okay. I mean, I could say like, okay, good. You can stick these triangles together in groups of 2. But what does that have to do with anything?
I mean, we okay. So we have this injective homomorphism from the rotation group into the reflection group. Index 2, injective homomorphism.
Uh-huh.
And that contravariantly induces a geometric morphism of toposes from the actions of the rotation group to the actions of the reflection group. So in other words, you can encode actions of the rotation group as actions of the reflection group. And so these irregular Coxeter tilings are actions of the reflection group. But that's but the ones that don't like the ones where you have to respect these larger fundamental regions that are 2 of the triangles stuck together, those are the ones that are in the image of this geometric morphism. I hope I'm saying that right. So
I wish you hadn't broken out the topos theory just then and it stuck to the language of groups, covering spaces, or covering spaces, and said something like any subgroup of the fundamental group gives you a covering of the base of that space. And here we have 2 groups, the whole fundamental group that's giving you the universal covering, and then this index 2 subgroup that I guess gives us like another covering that's like double covered by the universal covering. And I was hoping you'd like say something like why we especially care about this particular.
Sorry, I'm confused because when you said something about another covering, what do you mean another covering? What?
Doesn't any subgroup of the fundamental group of a space give you a covering of that original space?
A subgroup. Let me see.
This is like the Galois correspondence.
Right. Okay. Let me think what you're saying.
Maybe I'm getting it backwards. Maybe I'm doing something stupid.
Well, let me think. Just don't tell me. Let me think for a second. So let's see, there's a normal subgroup. Let me think. I mean, we're probably just saying the exact same thing in different language, but it's just your language is confusing me and my language is confusing you. So we have to struggle with this a little bit. Let's see. All right, so certainly subgroups okay, I think it's just a little bit of upside down confusion here.
Yeah, that's
so
probably true.
Right. You know, this is right. This is the universal one in one direction, but there's also the universal one in the other direction. I mean, there's the, you know, this is like the initial one. There's also the initial one, whatever. I mean, there's also the terminal
cover.
Right. This is the Cayley action, but there's also the terminal action.
Right.
And that just looks like the Riemann sphere with
yeah, the three punctured Riemann sphere itself, I mean, is the terminal cover of the Riemann sphere of that same space.
But there's the terminal action of the reflection group versus the terminal action of the rotation group. The terminal action of the reflection group just looks like a single triangle, and it sort of has reflecting barriers on the edges. Whereas the terminal action of the rotation group, that corresponds to, you know, this thing with, like I say, a single red-green edge, but two triangles, and they fit together. You know, one is the northern hemisphere of the Riemann sphere, the other one's the southern hemisphere of the Riemann sphere. So this is very annoying because I understand a lot of what the confusion is between the languages, and I wish I could cut through better here.
What I was wanting to know is just like, I can understand why it's important to think about the universal cover of a space, and in particular, the universal cover of the three punctured Riemann sphere. That seems like a very canonical, important thing to think about. But then you're also, and that's somehow connected to like the fundamental group of the space, which in this case.
Well, remember this, right? This is more like a universal branch cover, but okay, but.
Yeah, well, I'm temporarily removing those points.
Oh, okay, yeah.
So
then let's see, do I understand what you're saying? Let me
actually, maybe.
Yeah.
Well, actually, no, I am getting, well, okay, I'll say it better this time. So actually that that fundamental group is the rotation group. That's the Coxeter rotation group, the free group on two generators, is a sort of asymmetrical way to describe it. Then there's this bigger group, the Coxeter reflection group. And I'm wondering, like, what role does that play in this covering space theory? Why are we interested in two different groups here is my short answer.
All right. Well, first of all, let me try to explain one source of the confusion between us. So one thing is that you're doing topology and I'm doing combinatorics. Now there is some deep relationship between the topology and the combinatorics. I mean,
but I'm wanting to do
that.
Yeah, I'm wanting to do that because, I mean, if we were just talking about Coxeter groups, then I'd be perfectly content to say yes, both the Coxeter group and its rotation group are like really important things, and I think I sort of understand why they're both important. So from that point of view, Coxeter theory, then I wouldn't be asking the question like, why are we bringing in these two different groups? But there's also this covering space way of thinking about what's going on, or branched cover way of thinking about what's going on. And from that point of view, I'm used to, well, like for covering spaces, I'm used to thinking of there's being like one group to rule them all, which is the fundamental group. And then there are like tons of other groups for all sorts of other covers that aren't universal. But I'm not used to a situation where there's like two important groups, two very important groups.
Let me try to give you some vague idea, but I still don't like the direction you're going. I still think if you sort of listen to what I was going to say, then your questions would get answered pretty shortly. But let me try to answer your question anyway. So see, what's going on here is that if you deal with the rotation group, then you're getting relatively close to homotopy theory pretty directly, because the only thing that's funny about the covering spaces here is that they're branched at a single point.
3 points? What do you mean a single point?
At isolated points. They're branched at isolated points, a single isolated point, perhaps thousands of single isolated points.
Okay, yeah. Okay.
But if you're dealing with the reflection group here, then if you try to give a topological interpretation to what's going on, something funnier is going on, because you don't just have branching, you have folding. So there are these, and folding has some mysterious thing to do with the relationship between real geometry and complex geometry, and like
okay.
So yeah, right. So there's pure covering space theory, which is pure homotopy theory. Then there's branch covering space theory, which is just such a small step away from pure covering space theory that you don't even notice the difference. But there is a difference. But then if you start getting into this thing where the reflection group is involved, then there's actually, like I say, there's this more complicated, more exotic, more unfamiliar thing called folded or folded plus branched covering spaces or something like that.
Okay, so there were some
unfortunately, you're also getting into some very interesting, tricky questions, which I don't have good answers to, but are really fun to think about that. And you're slowing me down by forcing me to think about those. But go ahead. Yeah. What?
Okay. No, I can. Well, it's mysterious. Okay, so it's sort of mysterious, but I sort of get it. So I mean, something weird is that like you can take the universal cover of the 3 punctured sphere, and that, well, except for being sort of infinite, it's still like a complex. It's not a Riemann surface, but it's a complex manifold. The maps are the covering map is orientation preserving. But then you're saying like there's this other weirder thing.
Yeah, where the anti-holomorphic stuff gets involved. Yeah.
Okay, well that's okay. I can quit at that point. Yeah, I mean I feel like I've.
I still didn't give you a really good answer, kind of your question.
No, it's not a really good answer, but it's weird enough that I can sort of see why you're not going to give me a really good answer.
That's part of what's going on.
Okay.
Yeah,
so
and there really are good reasons for bringing in this topos theory and stuff. Um,
I'm not against it, but it didn't seem to be
well,
helping me at the moment. And
oh, okay, but let me give you an idea. Let me just right. Let me. Right, temporarily forget that there's anything involving homotopy theory going on here, and maybe even forget that there's anything about involving complex analysis going on here, and just think that we are developing a kind of notation for representing actions of certain groups as tilings. Okay. And so let me jump into the example in there. So for example, I'll just let's try to establish how to interpret either an action of the rotation group here or an action of the reflection group here. How to get a tiling from. Now, maybe, I don't know, maybe you think that's already obvious or something, but let's try acting it out in some cases, okay? Partially because I've had a certain amount of practice with this, but actually I haven't had enough practice. The last time I tried it, I still was having problems getting it to work. But so let's try to do some examples here. So in fact, let me try to see if I can semi-cheat here by doing an example that I was trying to get to work, if I can find it. Where is it? Where's that example here? That's not it. Where is it? Well, first of all, these pages don't look at, okay, yeah, pages are not numbered correctly. Okay, no wonder what the problem is. So, 79. Okay. Sorry, my papers are all disorganized here. I think this, I can find it now. Is that it, really? Okay, let's try that. So, okay, I'll draw a. So first of all, right, we can just draw an action of the free group on two generators easily enough. I mean, and yeah, I'll start making it a finite action of the free group on two generators. And there's probably some role to play both for the finite ones and for the infinite ones, but I'll just start out with the finite one here. So let's try. What does this one look like? A and B and C and D and E. Okay, so this could be an action on 5 elements, okay? And we're gonna have 2 permutations. I'll call them the green permutation and the red permutation, okay? So the green one will just go something like that, and like that, and like that. Okay, and the red one is much messier in the picture. So what does the red one do? It takes A to D. So let's see. So maybe you're telling me that I could just write this in a more schematic way or something like that. I could just say something like A, B, and C, D, E is one of them. And then the other one that I have written down here, the red one, is A goes to D, and D goes to B. I think I've seen this notation for permutations in, you know, some old-fashioned
Yeah,
textbooks. It may be a very standard notation. And then B goes to E. And then C is isolated. Okay, so that's the green one, and that's the red one.
uh-huh.
And I was trying to draw the red one in here. What does the red one do? It goes from A to D, and then it goes from D to B, and then it goes from B to E, and then it goes from E back to A, and then C is fixed or something like that. Okay. But now, how do we get a child's drawing from this? And I'm asking that as a question. Could you tell me, for example? I think I could figure it out, but do you have an idea how to do it?
No, I mean,
Okay, that might not be
doesn't
surprising.
sound impossible, but it
All right.
doesn't sound impossible. But
So first of all, let's try to establish the genus of this thing, because that might help as a little. It might actually be cheating. Probably you should construct it, theoretically, you construct it in a purely local way, and then you suddenly realize, oh, this is genus 17 or whatever. But it seems to me I've got, what, 5 points. And so in my Euler characteristic calculation, that counts as negative. And then
those points, what, I don't remember this child's drawing stuff nearly well enough. Are
yes.
those points over?
I mean, the point of what
infinity?
we're doing here is to sort of try to present it. But go ahead, yeah.
Well, yeah. Are those points going to be points over infinity or points over everything? So we're building a Riemann surface that's branched over the 3-punctured sphere, and you're talking about 5. You're focusing attention on 5 points, and those points are going to be in the covering space, I assume.
Can I think about that? They're not really points in the covering space. They're more like regions in the covering space or something like that. So
okay, that's fine. Yeah.
The green points are going to be the orbits of the green permutation. The red points are going to be the orbits of the red permutation. And the blue points are going to be the orbits of the blue permutation, which is, you know, the inverse of the product of the green and red or something like that.
By the way, I think you drew a blue blob next to the green permutation. Not that that matters so much, but
is that blue?
Is that green? That looks blue to me.
No, it looks blue to me.
Yeah. It's supposed to be green, right? You're not trying to.
Yeah.
Okay. You just suddenly got me scared. Okay.
Okay. Okay.
Okay. So there are 5 regions, and when I cross a green edge, I go from one region to another by doing one of these red or green things. Sorry, is it there are 5 regions, and crossing a border line is indicated?
That's right. So, sorry, I'm just distracted here because I'm suffering horrible indecision about which way to go here. Yeah, everything you're saying is probably right. Yeah, yes. I mean, yeah. I mean, there would be 5 regions, and you know, so it's probably 5 of those fundamental regions, and then you figure out how they're stuck together. And that involves looking at the corners and stuff. And, you know, like I say, the green dots are the orbits of the green permutation, blue ones are the orbits of the blue, red ones are the orbits of the blue. But sorry, I'm just acting in a totally disorganized way here perhaps because I am totally disorganized here. But I just realized that I really do want to go back to an original plan that I had here. I mean, this is important what we're going to do here, but I just realized that I really do want to go back to the plan of setting out the 3 Coxeter diagrams here. So
Okay.
let me just try to draw them pretty quickly here. So like I say, this is a very equilateral one. Equilateral because it's got the same marking on each edge, which is infinity. The next one is much more like a straight line. You know, so there's like a homomorphism from this one. This is what I mean by a surjective homomorphism of Coxeter diagrams. I mean, you can see that it has a homomorphism of Coxeter groups. So, right, one of the conventions for Coxeter diagrams is that, you know, the invisible edges you can think of as being marked with the numerical label 2.
Yep.
And that works in terms of having a homomorphism here, because infinity can wrap around 2.
Mhm.
You know, infinity means there's no constraint. 2 means that, you know, something is ordered 2. Yeah, so there's that one. So right, this we should call the child's Coxeter diagram. This one we should call the cartographic, or perhaps 2D cartographic. And then the next one is what? It's like, and I'm hope I'm getting the right conventions, or I'm hoping getting reasonably sensible conventions here, or that if I'm not getting this reasonably sensible conventions, that it'll be easy enough to fix it later on. So there's this one. So now instead of the edge being invisible, we have the label on the edge being invisible, and the convention for that is that's a 3.
Yep.
So does that all fit on one screen there? More or less. And this one we call the modular Coxeter diagram. Okay, so each of these has a regular Coxeter tile, where the tiles are actually the elements of the group, I guess of the Coxeter reflection group, but then, you know, neighboring pairs are, you can think of those as elements of the Coxeter rotation group. So there are these regular tilings, these universal regular tilings that sort of give the group itself, or you can think of it as the Cayley action of the group. But the irregular tilings that just respect these laws, but maybe very, very irregular, those are giving general actions of the group. And if they're finite, then the general finite actions of the group. And so, right, so we should really, really think of these as very analogous. And again, so these are group homomorphisms, but you can pull back the actions, right? Right, it's not just that you can, I mean, you could probably push forward actions and pull them back as well. But the point is that pulling back actions is a very nice thing. That's really that's the directions of the interpretations of theories.
Mm-hmm.
So that's the direction of the interpretation of theories, and that means that they are theory morphisms. Those interpretations of theories are theory morphisms. So they preserve Cartesian product of group actions, and they're also left adjoint. They preserve all the colimits. So they are. Right, you can actually, right, they're actually a little bit better than that. They are geometric morphisms. They preserve, I guess, all finite limits, and they preserve all colimits. So they are left exact, what are they called? Left exact, left adjoint, something like that. They're geometric morphisms. But
And you think of the sorry,
yeah,
you think of the direction of those as going backwards. I know there's like two ways to think about geometric morphisms, but
yes,
like you picked some direction, so you're going having them go back. Huh?
That's right. And that's the theory direction, the syntactic direction. You know, you think of these as syntactic categories. These are the directions. Yes, the pullback, that pullback direction. I mean, it's basically right. It's basically the contravariance of algebraic geometry. The group homomorphisms are going in the geometric direction, but in terms of on the syntactic categories, the sensible thing, that's, you know, that's the algebra thing. That's going in the algebraic directions. So these interpretations of theories, which I guess is that's the left exact, left adjoints. I always forget what left exact means, but I hope it means preserving finite products. Finite limits. Sorry, thank you. Finite limits. Yes, so it's important to think about what, I mean, like we said, yeah, yes, it's finite limits, but really important is the finite products. I mean, maybe we should also think about the finite limits, but let's first of all just think about the finite products and what is that interpretation of that here. So in terms of, right, that's just Cartesian product of G sets, right? Cartesian product of G sets. But what is the conceptual interpretation of that Cartesian product of G sets when we're anticipating that we're going to secretly be thinking of these things as like branch covers or folded covers or something like that? And in that context, what happens to this Cartesian product is it becomes fibered product over the combinatorially terminal action. So right, I mean, so for example, let's do the child's rotation group. So that's the free group on two generators. So, right, the terminal action for that is this, again, it's this thing, it's got two triangles. And, you know, so it's really the equator with three marked points on the equator, green, blue, and red, or 0, 1, and infinity. And, you know, the two triangles are sort of mirror images of each other. One is like the upper half plane, the other one is the lower half plane. And
Thanks. Yeah, that actually helped.
yes. And see, what we're actually doing is we're supposed to be doing Cartesian product, but it's more like fibered product over the terminal one. So it's, you know, it's pullback over the terminal one. So the different thing, yeah, it's the fibered product of these child's drawings. Thinking of them as, you know, living over the Riemann sphere. So, you know, over the Riemann sphere, there are these finite discrete fibers. So that really is important. You see what I'm saying? There is this very important.
So getting back to an old question of mine, is that,
yeah?
Wow, now I'm really confused, but I'll still ask it.
Yeah.
So are the 5 elements in that picture you had before, A, B, C, D, E?
Yes.
So those are, sorry, are we supposed to, I'll just say it. Are we supposed to be thinking of those as fibered over 0, 1, and infinity over that 3-element set? I'll say it.
I didn't even understand the question. Can you say this question more precisely? Are we supposed to be thinking of what? As what?
No.
Well,
So
say
you're
it
trying
again?
to, I'll just say it again. It's
Yeah.
starting to seem like a dumb question, but I'll say it anyway. So
Yes.
is that 5-element set A, B, C, D, E that you had drawn earlier?
Yeah. Yeah.
Is that favored over this 3-element set 0, 1, infinity? I think not.
No, it is like the, what am I trying to say? It's like the,
Oh, it's
it's precisely the thing that's giving you the generic fibers.
okay. So it's like fibered over this. Well, something like fibered over this 2-element set of triangles that you were just talking about. Although,
Yeah, I mean, it's giving the sheets over the upper half plane.
okay,
It's giving the sheets over the upper half plane.
okay, yeah, over one triangle, not two, over two, yeah, because it was connected to the child's rotation group.
That's right. That's right. So we're going to have like,
Okay.
Well, we're going to get back to that. We're going to get back to that thing that you're asking about really, really soon. But I think I have a few more remarks about the general big picture of these, this composite of Coxeter homomorphisms diagram, homomorphisms of Coxeter diagram. So, so this child's one is a very classic, hyperbolic Poincare disk type of thing, and we already drew it, right? Now the modular one, right? In a way, it's almost the same picture, but right, you have to be careful. There are traps to avoid falling into, or if you're going to fall into them, you should be aware that you're falling into them. So how does this work? Let's see. So it looks like rotating around the reds is infinite order. So the reds must be the cusps. So it's kind of the same picture as before, but now all the cusps are red. Instead of 3 different colors of cusps, we just have red cusps. But where are the blues and the greens? Well, the blues, well, I mean, you have to barycentrically subdivide now, right? To get the whole thing to make sense. You doing this right? Something like. I hope I'm doing this approximately correct. So where are the blues? The blues are at edge centers, which would be like there. Does that seem right? And the greens are at triangle barycenters, or whatever you call them. Something like that. Right, so it is a like a barycentrically subdivided version of the previous diagram, but you have to be careful about that, right? So like, what are we kind of saying? One of the things that we're saying is that right, there are at least two homomorphisms here that are relevant. Well, I mean, there's the composite homomorphism that we had here, right, which is a surjective group homomorphism. And since it's a surjective group homomorphism, it's giving us like what, a faithful, is that right? You know, the pullback thing, the geometric morphism going the other way. This, presumably there's some nice property corresponding to the surjectiveness of the geometric morphism. Is it faithfulness of the, I don't know, but I mean, what's right? There's the other homomorphism that's sort of implicit in the barycentric subdivision idea. So how does that work? What are we trying to say? We're trying to say that let's see. I mean, the regions over here are fundamental regions for the modular group. How does this work? Let's see. I mean, the free group on two generators is a subgroup of the modular group.
Yes.
And that is sort of visible in this picture in some way, but it's in a misleading way. Is that right? I mean, right. So, I mean, there's the well, there's this surjective group homomorphism, but then I think there's also this injective group homomorphism.
So the free group on two generators, is that also the modular rotation group?
No.
Oh, okay.
No. Okay. So what okay. So the modular reflection group is PGL 2Z. And the modular rotation group is PSL 2Z.
Okay, yeah.
And
sitting inside the ladder, there's a free group on two generators, I guess, that's sort of famous.
yes, but I'm getting confused about how that works, how it relates to, right? We have this picture, which is just like a barycentrically subdivided form of this picture up here, but with funny relabeling of the colors. And how does that work? I have a feeling that it's easy to get confused about the different homomorphisms here, but right now I'm not doing a good job of seeing how to avoid getting them confused. I'm in danger of getting them confused. So look,
I'll let you dodge it.
Yeah, but for us, the important homomorphism at this point is this composite one that we're drawing here, which is a surjective group homomorphism from the child's Coxeter group to the modular Coxeter group. or from the child's Coxeter rotation group to the modular Coxeter rotation group. So that would be going from, that's just saying that that's just saying that PSL2 comma Z has two generators. And that the extra relators just say that something is order 2 and something else is order 3.
Yep.
So that is saying that it's like a free product of Z mod 2 and Z mod 3. Is that a famous fact about PSL2?
Yep.
It's a free product. Okay, let me just write that down. So, okay. Is there some standard symbol for free product?
Yeah, star.
Okay, but free product of Z mod 2 and Z mod 3. And that we think is what? PSL? Yeah, I think that's what this is right here.
Uh-huh.
Okay. Well, so right. Saying a lot of things very badly, but there is something very interesting and important going on here, if we really understood it, about the way the Cartesian product of the group actions is going over to the fibered product of the branch covering spaces. So, okay. Let me make another big picture comment here about this composite homomorphism. So there are a couple of famous theorems connected with this child's drawings. There's a famous theorem called Baez, I don't know how to pronounce it, Baez theorem connected with child's drawings. And there's also a famous theorem connected with the modular curves, the modular drawings, which is the modular tilings, which is, I guess, the modularity theorem or something like that. Mm-hmm. And there's a striking contrast between how much work goes into the proof of those theorems, allegedly. Allegedly, there's a lot of work that went into the proof of the modularity theorem. And you can tell that because it actually succeeded in proving Fermat's last theorem or something like that.
Yeah.
But Baez's theorem is supposedly notable for being easy to prove, surprisingly easy to prove. So in a way, they seem to be very analogous theorems. So, I mean, right, it sounds, I still don't understand either of them that well yet, but right, there's some funny parallel between them, it looks like, which clashes with the idea that one seems really easy to prove and one seems really hard to prove. I mean, at one time I thought that I was in danger of thinking that, you could prove the hard one just by proving the easy one, but I don't think that's true. So, I mean, let's try to get some sense of what the two theorems say. So the modular ones, the modularity theorem says that you can get, I guess, any elliptic curve. So just, I guess it's only about genus 1 case. But maybe it says that if it's defined over the rationals, then you can express it as one of the tilings, one of these modular tilings. Whereas Baez's theorem says, so it works for any genus. Is that right? And it says that if it's defined over the algebraic closure of the rationals.
Hold on just a second.
Okay.
Oh, I didn't know you were talking to people. Sorry.
Okay. Never mind.
Never mind. Nothing important.
Go ahead.
So it says that right, Bayes' theorem removes the restriction on the genus. It relaxes the restriction from being defined over the rationals to being defined over the algebraic closure of the rationals. Does that sound right?
Yep.
But to pay for that, it says that instead of being able to draw it as a modular tiling, you can only draw it as a child's tile. So I really would like to understand the proofs of both of these theorems, but right. So right, I mean, I think I asked you one time a couple of decades ago, why you can't just prove the modularity theorem by the Bayes theorem. But right, it's clear that it's going the wrong way, right? I mean, if you're trying to, what am I trying to say? Any modular tiling is automatically a child's tiling, but not the other way around. So it's the easy theorem doesn't really. There's no obvious way to use the easy theorem to prove the hard theorem. It might be more like the other way around or something like that.
You're making me wonder if there's a cartographic version of the theorem.
Yeah. So, okay, let me say some random comments about the cartographic stuff. So when I was just beginning to try to learn from the Schnepp's book on child's drawings, they started talking about child's drawings. They called them clean child's drawings and pre-clean child's drawings. And they sounded like they were really the cartographic child's drawings or something like that, because they said something about, I think they were saying that when the blue dots have exactly two things coming out of them or something like that. So I mean, we might have to read some of the, who is it, Jones and Singerman or something like that. We might have to read some of what they're saying about, I think they talk about the cartographic stuff, don't they? I don't know. But
yeah.
I mean, right, from one point of view, the cartographic thing, it's just a funny stopping off point in the middle of this process of going from the child's thing to the modular thing. Right, so part of what's going on here is, right, the whole idea of cartographic stuff that's really related to this, right? That's really related to this whole idea of barycentric subdivision, which sort of creates some of the confusion between the different ways of relating the child stuff to the modular stuff. So, right, I mean, like, the cartographic stuff is about like polygonal tilings, but where you reinterpret a polygonal tiling as a triangular tiling by barycentrically subdividing a polygon into triangles.
Did you say barycentrically subdivided? I mean, you sort of, yeah, I don't know if people call it that, but
Yeah.
yeah. But I think I know. You put a dot in the middle, and then you create a whole bunch of right triangles.
Yeah, I wouldn't be surprised if it isn't. I wouldn't be surprised if it is barycentric subdivision.
Yeah, actually, you're right.
It
might be.
Yeah, in some hyperbolic sense. I don't know. I don't know. Yeah, but I was tempted to call it right. I didn't even think about what barycentric subdivision meant.
I guess if you mean by barycentric subdivision, if you mean like
it's like a combinatorial
the
version.
face post set.
Yeah.
Put a dot for each thing in the face post set, then I guess it is, yeah.
Yeah, some combinatorial version of barycentric subdivision or something like that.
Yeah.
So yeah, I think mostly we're going to avoid the cartographic stuff in the middle, but I just can't resist saying a few silly things about the cartographic stuff in the middle of this composite of Coxeter. So the one at the top, the child's thing, that is a paracompact. Is that what it's called? Paracompact?
Yep.
Paracompact Coxeter diagram. The one at the bottom, the modular one, that's also paracompact. I think the cartographic one isn't paracompact. Now, I don't know what that means. I mean, can you still, when you draw the universal cartographic one, can you think of it as having any kind of geometric structure at all? I mean, like, right? I mean, these compact ones are like Euclidean or something like that. So there's like a quadratic form, this Coxeter form or something like that, that has unmixed signature.
Mm-hmm.
When you get these paracompact ones, they're sort of like Lorentzian. There's, a single dimension of time going along with the dimensions of space. When you go beyond paracompact, can you still think of it as like being a quadratic form and a signature, but the signature has more than two things in it? Is there like
there certainly are a bunch. People do certainly think about those. That is.
So I'm wondering if the 2D cartographic group has an interpretation like that. So that would be what? You would have to look at space-time. I don't know, right? I mean, right now, even the sphere would itself have mixed signature, right? When you have mixed signature, then the sphere still has pure signature. But now maybe we're getting to a situation where even the sphere has mixed signature, and the sphere is the thing where the tiling is living. I don't know. That's just a random silly idea I wanted to throw out there. I'm curious about what happens if you try to give a geometric interpretation of this universal cartographic thing. I haven't actually read up on what people would do with that, but I'm pretty sure it's not paracompact. Doesn't it seem like it's not paracompact? I'm sorry to just, boy, that's funny. How can the first one manage to be paracompact when the second one doesn't manage to be paracompact?
I have no strong intuition for whether the cartographic one is.
Yeah, so don't trust me on that. But I'm guessing right. For all I know, maybe the cartographic one is paracompact. But I thought something funny happens when you try to draw the universal cartographic thing. But I honestly don't know. I'm having trouble right? If I'm having trouble imagining that it's going to fit on the Poincare disk somehow.
So you'd be like tiling the disk with infinity gons, all of whose vertices are at infinity, with like infinitely many meeting at each vertex. Is that what that is?
Something like that. I mean.
I don't know if that's right, actually. I don't know if that's
yeah, but it's the same kind of confusion that I run into when I start thinking about it. So I don't, let's not think about it right now because I don't think anything else to say about it. We're sort of running out of time. So let me try to get the stuff that we're supposed to do here. So I guess, right, the stuff that we're supposed to do here is some of the stuff that we're supposed to really do here is to really understand, back this stuff that we're trying to do here, where we take, right, we take the purely combinatorial idea of just an action of the free group on two generators. And again, this has very analogous things for the modular group and for the presumably for the cartographic group. But I'm going to focus on the child's drawing case here. So we're just taking a pair of permutations, an arbitrary pair of permutations of fine. So I guess you're telling me that if I really want to do the modular case, I should just make sure that the arbitrary pair of permutations, that one of them is order 2 and the other one is order 3.
Yeah, I guess so.
And from that, I should be able to draw the modular curve combinatorial.
So last time we were doing a whole bunch where we were doing a whole bunch of pairs of permutations where you had like a rectangle of dots and one permutation just slid everything over to the left and the other slid it all down. So that's like,
right. That was just basically where the two permutations commute with each other.
Right. Yeah, that's, yeah.
Roughly speaking. And right, and that's sort of interesting because it connects with, art and reciprocity, which is about B and extensions and things like that. But I also realized that, a lot of this intuition about working with the permutations just is much better just thought about without having the permutations commute with each other. So yeah, so I'm trying to, let's see if we can do this example here. So well, first of all, like I say, I was cheating and doing an Euler characteristic calculation with this. So I think for the Euler characteristic, I think I get -5 plus 2 plus 2 plus 1. So 5 is the number of the points here. And again, this is the same, when I acted out something like this last time, you told me that this was basically Riemann-Hurwitz formula or something like that. I think that's what you said.
Yeah, it was. Why are you getting negative instead of 5?
-5 instead of +5? Because these are the things that are the sheets over the upper half plane. So I mean, I'm thinking of it, right? I'm thinking of it from Shanuel's point of view instead of from the Riemann-Hurwitz point of view.
Why did I thought it got negative numbers for odd dimensional things? The Euler characteristic.
Well, it has something to do with the thrice punctured sphere is itself Euler characteristic -1. Right, because the right. I mean, it's like,
I see one copy of that. Okay.
Yeah, that's right. That -1 is the leftover from the.
Okay.
You've got Euler characteristic 2. So if you put 3 punctures in it, you're now down to Euler characteristic -1.
Okay. So you get -5. You get 5 of these thrice punctured sheets.
Yeah, something like that. Yes.
And then what's the 2 and the
2 orbits of the green permutation over here, AB and CDE. And 2 orbits of the red permutation, which is ADBE and C. And then there's just 1 orbit of the composite permutation. If I did it correctly, I think I did it correctly. So that seems to be coming out to Euler characteristic 0, which would be genus 1. So it looks like this is going to be a Giles drawing on a torus. So maybe we can try and do it that way. Okay. What?
Okay.
Okay. So I have to draw 2 green dots. Well, so okay. So maybe I can call this green dot. I can call it F. Sorry, that was supposed to be a different color. Did that come out right? F and G, and then H and J. And then I'm pretty sure there's just 1 blue dot, so I'll call that K. So why is it screwing up? Blue. Okay, so it's like a blue thing, which is K. Okay, so there's got to be something like F and G over here somewhere, and H and J. And then there's a K, a blue K somewhere. Not sure where to put it. I'll put it in the middle. I'm not sure that's a good place for it. Okay. And now, where are the five things? So let's see, there's an A, there's A, B, C, and D. So A goes from F to H, is that right? So that's like A. And B goes from where? B also goes from F to H? But the thing is, I'm not sure whether it,
I don't know how you're doing that, but it sounds like you're saying because A is sitting inside the same orbit of the F, sorry, permutation. It's sitting in the F permutation and it's sitting in the F orbit of the green permutation and the H orbit of the red permutation. You just draw this A there.
yes, I think you're probably understood it as well as I do. I'm just taking guesses at this point, but it seems pretty reasonable.
Okay, it doesn't seem. It seems, I think I'm like a kid learning how to do long division. Okay, so that's what you do. Okay, I'll do that.
So
Yeah,
so I think the B is also going from F to H, but I'm not sure whether it, travels around the world or something like that. So maybe I won't draw that in yet. You
can draw it and redraw it, but yeah. Okay.
And well, maybe we should actually already try rotating A a little bit. So if you rotate A around F, then what should happen? So you keep F fixed. What happens?
Rotate A around F, so the A turns into B. Is that what that means?
Well, if we're rotating it around F, I thought that meant that, well, F is going to stay the same, so it still has. Oh, that's what you're saying.
I'm confused, but I'm just imagining now you get like edges coming out of F.
You know what? It sounds to me like you're saying it's something like this. That does it have to do that or something like that? What am I trying to say? Well, okay, right. We're not supposed to draw it, right. We're not supposed to draw in the connections between blue ones. But right, I mean, if you rotate, so this would be B here or something like that.
Okay, well, anyway, I think I can see what the rules are, even though I don't get why. I could probably check afterwards to see if this makes sense. So if you start rotating around H, you drew the A and the B, but somehow in between them there should be a D.
Yes, but okay. I think this does actually work. When you clean this up, it does actually work, I think. But let's try a more systematic, more clunky way of doing this. Okay.
Okay.
Let's switch from the child. I was trying to actually draw the child's drawing, but let's try to draw the child's tiling instead of the child's drawing.
Okay.
So, right, that means that we're going to have these 5 triangles, which are I'll think of it as going clockwise from, well, I guess from green to blue to red. And so one of them is A, with the green being what? F. And the blue, the blue has to be K, I think, and the red is H. Okay, and then there's the one for B, which is what? It's got the green is F, and the blue is K, and the red is H again. Okay. And then there's these other three. Okay, so there's C and D and E. Maybe I'll even try to put in the colors. So there's a green there, green there, green there, green there. There's a red there, red there, red there, red there. All the blues have to be K. There's just one blue. You know, I'm a little bit confused about this. It seems like we only have one blue. And I thought you were trying to prepare me last time for the idea that when there's just one blue, just one infinity or something, that it's end up being like a tree or something, and then it would be genus 0. But here we're definitely getting genus 1. So I must have misunderstood something about that. But anyway.
Where did you get the fact that there was one K, one blue?
Well, I actually, somewhere to the side without showing you, I composed these two permutations, the green one and the red one.
Oh.
And I'm pretty sure I got a single orbit when I did that.
Oh, okay, yeah. Okay.
Being very sloppy about writing that down, but that's what I think. So let's see. So these are all K. The blues are all K. But what are the greens? The greens are C is in G. Is that right?
Yeah.
Oh, these are all in G? And most of them are in H, except for C. And C is in J or something like that. So it's got these 5 triangles. Now, right, you have to remember that these are the 5 triangles that are all clockwise. So you know what I mean? These doesn't include their mirror reflections. So you have to start gluing. What?
I just said, okay, twice as many. Okay, well, I was worrying about that because we just had one triangle with a vertex J.
Yeah, I'm going to put a big question mark in this picture because I don't know if I was doing it right there. Go ahead. What? Yeah.
We have just one triangle so far with a vertex called J, and that seemed awfully few. So, but if we had 2, then I guess we can get some reasonable shape out of this stuff.
But how does that work? I guess you're telling me it's something like
they all like mirror image ones are the ones we have.
Well, I think you're telling me that it's something like this. Let me try. I think you're telling me that it's like this. With J is right there. And something like that.
Yeah, that's my wild guess. I'm just like completely winging it.
Right. Me too.
I don't think you're winging it as much as I am. I hope not.
Well, but you're better at winging. So,
it's
yeah,
like
I mean,
if you have a student instructor and trying to fly a plane, and then like you discover that the teacher is like also a
That's right.
student.
That's right. That's right. So like somehow I'm imagining we're supposed to take these 5 triangles and we're supposed to sort of like glue them together like this. And somehow that's, supposed to automatically leave the 5 mirror holes that they're supposed to fit together somehow like that. And yeah, so this still needs to be cleaned up, but yes, I mean, right, so I mean, this is supposed to be progress. This is supposed to be progress. This is supposed to be teaching us how to, how to understand what a child's drawing really is. A child's drawing is really just an action, perhaps a finite action, but you may want to include the infinite actions as honorary things as well, ideal limits. These things actually do come up. I mean, it's like these, this thing that looks like this thing down here, people sometimes consider this to be a sort of honorary modular curve. It's like a limiting thing, and you can talk about the modular forms that live on it and stuff like that. And it's like the modular forms that live on it, I guess, is a big inverse limit or a big direct limit, whatever. Well, but also, right, I mean, so, right, again, from the topos theory point of view, sometimes people make a topos out of the finite actions of the free group on 2 generators. Sometimes people make a topos out of all the actions of the free group on 2 generators. And there's presumably very interesting interactions between those two. Which way does the geometric morphism go? I have to think about it, but it's supposed to be conceptually obvious. And, one of those corresponds to like a profinite group. Maybe that's like a profinite completion. Is there such a thing? I'll have to think about that. That would be interesting. But yeah, so I mean, there's this topos of finite actions of the free group on 2 generators. We have a combinatorial way, we have all sorts of combinatorial ways of drawing that, but including the sort of child's drawing way of combinatorially drawing that. And we're just trying to understand at this point, we're just struggling to understand how that works. And yeah, well, okay, so we're running out of time here. So maybe, well, let me, again, as usual, let me try to think if there are any really crucial punchlines that I can remember before we quit here. But maybe not. Maybe this is kind of, the punchline is just that we're learning how children's drawings work. So let's see. I mean, there's all sorts of things that we should be anticipating here, right? But
yeah, there's lots and lots of stuff.
Right.
Like,
I mean, yes, go ahead.
Like, for example, that the child's, I mean, there's all sorts of weird stuff, like the child's drawing Coxeter group maps onto all the 3-dot Coxeter groups. And somehow going down to the one sounds promising because those are both connected to number theory, but there's like all these other things you could conceivably investigate.
You're talking about these 3 Coxeter diagrams that we're talking about here?
Yeah, I'm saying the child's one is sort of the universal 3-dot Coxeter group.
Yes,
that's
true.
If we ever understood what we were talking about, then we could like expand the scope of investigation by looking at it mapping onto other 3-dot Coxeter groups and figuring out they should be part of the story too somehow, in some extended version of the story. So it sounds a little surprising to me, sort of, although maybe not, since like Klein was messing around with different Coxeter groups when he was studying curves. Well, like the icosahedron and Klein's quartic and stuff.
You know, now I'm not even sure if the children's one is paracompact. I don't even know what paracompact means. I might have to investigate what paracompact means, but I don't know whether the children's one is paracompact, and I don't know whether the cartographic one is paracompact. But I'm pretty sure the modular one is paracompact, whatever that means. One thing that we were doing last time was we were playing with the abelian child's drawings. And one of the things that was really easy about the abelian child's drawings is that, you know, when we got into, if we get into practice, it should be very easy to draw them and understand what they are, what they look like as pairs of permutations, but also what they look like as child's drawings. But you pointed out that it's really easy to give very explicit descriptions of them in terms of, you know, an equational presentation for the curve.
Right.
And what about these non-abelian ones, right? I mean, again, Baez's theorem seems to be saying that, oh yes, you can easily, whatever, I'm not sure easily, but it says that you can interpret any one of these child's drawings as an actual curve. And how, right, okay, so right, we right.
How do you actually get it?
Right, I guess that would amount to actually trying to learn Baez's theorem. And do you have any ideas about that? Is there any obvious?
Not enough, no. I mean, I was trying, once I was thinking like, someone was saying they're like, oh, Grothin got very excited by this theorem, which is surprisingly easy to prove.
Yes.
So then I like try to look at some proof of Baez's theorem.
And it wasn't
that surprisingly. It was short, but it referred to like 2 other theorems that I didn't know about. And I don't remember how constructive it sounded. It didn't sound as constructive as what you seem to be hoping for now. It's like, it'd be really
right.
cool
I'm sort of hoping
like,
I'm hoping for something very nice and constructive here.
Yeah, that would be great, but I don't know. Yeah.
Anyway, so yes, well, right. So one of the things I want to do is actually, you know, further explore the abelian child's drawings, and again, also the relatively abelian child's drawings, right? You can start with any child's drawing and then take the relatively abelian ones above that and try to analogize that to what's going on with the Artin reciprocity theorem, where you study relatively abelian number fields that are, you know, abelian extensions of some other number field. Probably all sorts of things I'm forgetting to say, but I guess we'll just have to leave it there for now. I hope this was useful.
Yep.
I hope the main use was getting more comfortable with very concrete ways of turning pairs of permutations into official child's drawings. Maybe not completely comfortable yet, but that's what we were trying to do today.
Yeah.
Okay. Okay.
Okay.
I'll see you. Thanks a lot.
Yeah. Yep.
Okay. Bye.
It always calls. These are always demanding a next episode here. Yeah. So.
Sure.
Yeah. Which is fine.
Okay.
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 See you.
I'll see you.
See you. Yeah.